Hi, all. It's Mrs. Blasky. Today we are going to talk about topic 0.7 and 0.9 about stoichiometry. So the process of using conversion factors should be something that you're pretty familiar with from first year chemistry. Stoichiometry shows up everywhere. It's just a tool that we use to figure things out. It's not even its own separate questions, really. It's really going to be something that we're going to use throughout the entire year. So I want to make sure that everybody is comfortable with the process and figuring out what the question is asking and how to accomplish what the question is asking. So at the beginning of topic 0.7, we've got your stoichiometry pathway, the map, whatever you want to call it, but how to go from one point of information to another point of information. The full pathway starts with grams of one chemical. We convert it into moles of that chemical. We then can use the mole ratio to convert from moles of one chemical into moles of a different chemical, and then use that new chemical's molar mass to get it into grams. Now, we are going to be able to manipulate this some. If we're talking about gases, we have to change it a little bit. If we're talking about solutions, we have to change it a little bit, but it's still the same basic pathway. Also remember that you can swing Avogadro's number into there anywhere if we need to convert into particles or atoms or molecules or ions or any of that sort of thing. So I'm going to just walk through one with you just to make sure that you remember how to do it. There's a bunch of examples in here again so that we can keep track of what's going on. So let's do example number 23. This one is a little bit different. So it says, how many moles of lead 2 nitrate will be needed to form 33.2 kilograms of lead 2 chromate? So what they're asking us to find is how many moles of lead 2 nitrate. That's what is missing. And what is given is 33.2 kilograms of lead 2 chromate. So now I need to figure out which chemicals these are and where they are in my balanced equation. Always make sure that your equation is balanced ahead of time. If I look at this one, it is not. I've got one lead, I've got 2 nitrates. I need 2 nitrates. I got 2 sodiums, I got 2 sodiums, I got 1 chromate, I got 1 chromate. Okay, so we're good. That was a pretty easy one to balance. Lead 2 nitrate is this guy. So we're trying to figure out how many moles of that one we need. And if we're forming 33.2 kilograms of lead 2 chromate, well, lead and chromate are here. So I'm starting with 33.2 kilograms of that guy. So anytime you're doing stoichiometry, you start off with a number that they give you. So I've got 33.2 kilograms. Also, always make sure you label it with what the chemical species is. So I have PbCrO4. That just makes sure that you're following all your units the right way, using the right conversion factors as we follow along. Now, this is kilograms. Normally when we talk about molar mass, we're not talking about kilograms, we're talking about grams. So we can do a quick conversion. Now, in AP Chemistry, I never need to see basic metric conversions. If you want to write them into your stoichiometry, into your conversion factors, you can, but you don't have to. If you could just all of a sudden in your head, I know how many grams that is, then just write it down. But if you need to show it in your work, please do. All other work needs to be shown out. You need to show your math. You need to show all the steps. You need to show everything written out. Otherwise, you will not get full credit for anything. I promise. Right? So kilograms, we can say 1 kilogram is 1,000 grams. If that's a conversion you don't remember, kilo, milli, centi, those 3 metrics are things that you should always know. All right, so kilograms cancels with kilograms. I've got grams up top now. What do I need to turn grams into? I'm going to change grams of PbCrO4 into moles of PbCrO4. So 1 mole of PbCrO4, I need to go to my periodic table and add together the molar mass. So if I find my periodic table, lead is 207.2, chromium is 52, And then 4 oxygens, oxygen is 16 even, means that my molar mass is 323.20 grams. So now the grams up there cancels with grams down here. Now what am I trying to get to? I'm trying to get to moles of lead 2 nitrate. So if I have moles of PbCrO4, the lead 2 chromate there, I want to turn that into moles of my lead nitrate. Those numbers come from my balanced equation. Those are the coefficients from my balanced equation. We call this our mole ratio. So the coefficient in front of the lead chromate is a 1. The coefficient from the lead nitrate is also a 1. Now, we could do another step after this and change it into grams of lead nitrate with the molar mass, but that's not what the question is asking for. The question says how many moles of lead nitrate. So I need to stop there. So I take 33.2 times 1,000 divided by 323.2, and I get an answer of 102.72277, blah, 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 blah. Thinking about sig figs. When we do calculations, we got to think about sig figs. This is the only number given to me from the problem that is going to control my sig figs. Metric conversions, this is an exact value. That is not going to have any influence on my sig figs. Neither will molar masses. So I've got 3 sig figs in my given number. I need to keep 3 in my answer. So that's going to round up to 103. If I look at my units, the units there should be moles of the lead 2 nitrate. Always make sure you're checking the balanced equation. Always make sure you're checking what the question is asking for and what it's given. Those units will really control how you manipulate your numbers. Now, we also have the idea of limiting reactants. Sometimes we're given the quantities of 2 or more of the reactants. We need to figure out which one is actually getting used up completely and which one is in excess. This is a concept that we're going to use a lot in AP chemistry about the fact that we don't always use up all of our reactants. Easiest way to do a limiting reactant question is to crank through the stoichiometry with both reactants and figure out which product is the smallest amount. That one is the actual answer. I'm not going to work through this right now. Again, we'll practice some of these in class. The other thing that we see in here is percent yield. This does show up on the AP exam sometimes, and it's an important thing to know. When you calculate stoichiometry, the amount of product that you calculate as being the answer or what comes from that particular reactant is what is considered a theoretical yield. That's what the math tells us. Theoretically, that's how much we should be able to make. In the real world, most chemical reactions don't actually make that much. There's all kinds of things that can go on with it. It explains it up in here. And it doesn't necessarily mean that something has gone wrong. It just means that some reactions don't form 100% of the products that they could. Sometimes it's part of the reaction. Sometimes there's another side reaction happens that another product forms sometimes. We'll talk more about that later on when we get to equilibrium. Sometimes you just don't get enough of the products or enough of the reactants reacting to each other towards the end of the reaction when those reactants are in low concentrations. Maybe there's just not enough collisions between the particles to form more product. It's totally fine. It's a fact of life. It happens. But we can figure out what percent yield we actually got if some data is given to us about a lab experiment, or this is a calculation that we can always do doing a lab where we say, well, in lab, we only got 2.5 grams, but the stoichiometry told me I should have gotten 5 grams. What's my percent yield? So, for example, in example 31, we've got a balanced equation. They tell us how much reactant we started with. What is the theoretical yield of oxygen gas? That's doing stoichiometry. Then it states the experiment is performed and the oxygen gas is collected and its mass is found to be 14.9 grams. That is an actual yield. That's how much we actually got in the lab. So to find the percent yield, we would take that 14.9 grams divided by whatever the stoichiometry calculates that we should get for the oxygen gas. Multiply it by 100 to get our percent yield. Okay. So there's some practice problems for that. I'm also going to tie in section 0.9 into this also, talking about molarity. Now, molarity is something that we covered in first year chem. Molarity is the measure of the concentration of a solution. So it's the moles of solute divided by the liters of the total solution. Calculating that out shouldn't be a big deal. You gotta convert some things into moles. Maybe we gotta convert some things into liters. Notice it doesn't say milliliters in the equation, it says liters. The conversion is that 1 liter is equal to 1,000 milliliters. Make sure that that's a value that you know. Once we have those molarities, we can actually use that in our stoichiometry pathway. So previously we talked about this pathway, going grams to moles to grams. What if we don't have grams? What if we have a volume? We could say, I have 50 milliliters of a 0.5 molar solution. How much product do I get? Well, because we've got that moles in there, molarity is an easy way to convert into the moles of chemical that we have. So for example, if we look at number 41, it says calculate the mass of the precipitate formed when 125 milliliters of a 2.22 molar lead to nitrate solution is mixed with excess sodium phosphate. So it says excess sodium phosphate. So that tells me that this sodium phosphate is in excess. I don't have to worry about that. This is not a limiting reactant question. But I've got 125 milliliters of a 2.22 molar solution of the lead nitrate. And I want to know the mass of the precipitate formed. That's what they want me to find. Well, I've got two products. Which one's the precipitate? We got to think back to our rule about what is soluble and what is not soluble. Remember the SNAP rule? Sodium is always soluble. Nitrates are always soluble. Ammonium is always soluble. And potassium is always soluble. So lead phosphate doesn't have any of those chemicals in it, but sodium nitrate has got the sodium and the nitrate in it. This is going to stay aqueous. This is going to be my precipitate. So I want to know how many grams of this are being made. So my given numbers, the 125 milliliters of 2.22 molar solution, I'm going to use that as my first steps of my stoichiometry. If you start with the volume, 125 milliliters. Now, again, we can put this conversion into our stoichiometry, or if you could automatically figure that out into liters in your head, that's fine. There's 1,000 milliliters in 1 liter. Now, if I've got liters on top, liters has to go on the bottom. My molarity, remember the units for molarity are moles per liter. So I can use that molarity as a conversion factor because 2.22 molar means 2.22 moles for every 1 liter of that lead nitrate solution. Now it goes on like a normal stoichiometry. Liters cancels out. I've got moles of lead nitrate. So I can turn moles of lead nitrate into the moles of the lead phosphate that I'm trying to find. I never checked if this was balanced, and it's not. My goodness. All right. So let's see. I've got 3 sodiums here. I need 3 sodiums there. I've got 2 phosphates there. I need 2 phosphates there. Oh, that's going to mess this up. That means this has to be 6. I've got 3 leads and 3 leads. That's 6 nitrates and 6 nitrate. Ooh, that works out. All right, so my coefficient in front of the lead nitrate is a 3. Coefficient in front of my lead phosphate is still a 1. And they want the mass of the precipitate, so that means I got to go to grams. So 1 mole of my lead phosphate, and I got to turn that into grams. Phosphate. So again, I go to my periodic table. Lead is 207.2, and I've got 3 of them. Phosphorus is 30.97, and I've got 2 of them, right, because of that 2 outside of the parentheses. And then I've got 4 times 2 is 8 oxygens. Each one is 16. That's a big molar mass. It is 811.54. Remember, please do not round off molar masses. So now if I do the stoichiometry, or I multiply everything, I got 125 divided by 1,000 times 2.22 divided by 3 times 811.54. Gives me an answer of 75.06745 grams. If I look at my sig figs, now I've got 2 given values, 125 and 2.22. Both of those have 3 sig figs in them, so I need to keep 3 sig figs in my answer. So this would round to 75.1 grams of my lead phosphate. So it's still stoichiometry, we've just got a little bit different way of being able to figure out those moles at the beginning. Again, we're going to keep working on this in class. This is something that we will be using all year long. If you're having trouble, let me know. I'll be able to help you out. We'll practice it a little bit in class. And we'll move on from there. I will see you next time. Bye.